Hello and welcome to the last lab. So this lab will be about depth first search and Tarjan. And it will have like three parts, three algorithms. First the depth first search, then the topological sort, and finally Tarjan. After that you need to do the evaluation for the depth first search, to count operations, and finally figure out the complexity. Let's go! So first, let's see, since depth first search is a graph algorithm, we need to store somehow the nodes and edges or arcs. So in this lab we'll work with oriented graphs, so we'll have arrows, not lines, and for each node we'll have a list of neighbors. And we can use the data structure from the previous lab. So previously we had a node which had a position. We won't have a position anymore, we will have a key, a number. And each node has an adjacency size, or the number of neighbors. For example, 0 has one neighbor. And for each node we can have an array of neighbors. Previously it was a double pointer, but it's easier if you just put it like an array of pointers. And each node will have a color. We'll see what's that useful for, and the distance and parent, we don't care about them. Okay. So let's see how it actually looks like. So these are our data structures, and here we have the nodes, and each node is at an address. So node 0 is at address 50. Here we can see that the node has the key 0, it has one neighbor, and his neighbors are 100, which is node 1. And its color is white. Initially all nodes are white. For node 1, here we have key 1, it has two neighbors. We don't count 5 as a neighbor of 1, because from 1 we can't go to 5. And its color is white, again. If we look in the computer memory, at address 50 we see the key 0, one neighbor, which is 100, and its color white. For node 1, at address 100 we have key 1, two neighbors, which are 200 and 400, and its color white, and so on. Anyways, this isn't as important, just as an image where addresses come from. Alright, so basically we'll use what we had from the previous lab in bfs.h, I think was the file name. Alright, now let's get to the important stuff. So here is how depth first search works. Let's say we are starting from node 50, from node 0, which is at address 50. So the first thing we do is color the node to gray. Then we take each neighbor. In this case the neighbor is 3, and we check if it's white, if it hasn't been already visited. And if it hasn't been visited, we call recursively dfs visit on the new node. And here from 3 we again color it gray, look at its neighbors and find 2. Again, for 2 we make it gray, we find its neighbor 1. But here for 1 we have this neighbor, 0 neighbor. The issue with this neighbor is that it's already been visited, so it's not white anymore. In this case, we just ignore it and move on to the next neighbor. Get 5. Here the neighbor is white, we haven't visited it. Here again at 5 we will look at 1 and see it's been visited already, so we don't go there. We move to 8. From 8 we can't move to 5. So at the end we change the color to black. When we finish visiting a node, when all of its neighbors are done, we make it black. And since the function returns, it will go back to the color, which was, so DFS visit of 8, of node 8, was called by DFS visit of node 5. So we go back at 5, we see it doesn't have any more neighbors, we make it black. For 1, we see it doesn't have any more neighbors to go, we make it black, and so on we go until we make every node black. So basically we recursively call on each non-visited neighbor. But in here we see that we only visited this part of the graph, and nodes 4, 6 and 7 aren't visited. So what we'll do next is, instead of calling depth first search visit only for 0, we will call it multiple times. So we will look at 0, see it's white initially, so we start the visit and visit everything. Then we take node 1. We check if it's white, and it's not white, it's already been visited, so we skip it. For 2 we skip, 3 skip. At node 4 we see that it's white, so we start a depth first search from it and move on to 5. For 5 we skip, for 6 we need to start a depth first search visit, and for 7 again, same thing. So basically we will create another function DFS, which initially makes all the nodes white, and after that it takes each neighbor, actually each node, and if it's white we start a depth first search from it. Alright. So at this point I suggest you put a pause and implement the depth first search algorithm. And after you finish, we can move on to the topological sort. Let's see first what this is. So the topological sort is useful when all the nodes are tasks. So in this case we want to build a house, and we have the following tasks. We have to buy materials, to build the foundation, build the walls, add windows, the roof, and put some paint. And arrows represent dependencies. So before you build the foundation, you have to buy the materials. Before you build the walls, you have to build the foundation. Before you add the windows, you need to build the walls, and so on. Now the question is, in which order can we make all the tasks so we respect all the dependencies? One example would be buy materials, then build foundation, then build the walls, windows, roof, and paint. This is okay. This is a good topological sort. This is a good topological order. Another order, which is the same as good as the previous one, is buy materials, foundation, walls, but this time roof, windows, and paint. It doesn't matter the order in which we do this, because they don't depend on each other. But a bad order is by materials, then roof, and only then foundation and walls. Because the roof needs to be done after the walls, but it's done before the walls, so that doesn't work. And now in our case, we only have numbers, so it's the same idea but only with numbers. So here we have 5, 0, 1, 2, 3, 4 as a good order, and 5, 3, 1 as a bad, or 5, 3, 0, 1 as a bad order, because 3 should be after 1 and 0. Alright, so let's see if the depth first search is good for topological sort. Let's just try to do a depth first search. So we start from node 0, then we go to node 1, then we go to node 2, then we finish with node 2, start with node 3 and end, start with node 4 and finish, because it doesn't have any more neighbors. And since 1 doesn't have any more neighbors to go to, we finish with 1. And for 0 we don't have neighbors, we finish. And we're done with the visit from 0. And then we look at 1, it's already visited, 2 is visited, 3 is visited, 4 is visited. Then we look at 5 and see it's white, so we start another depth first search from 5 and finish it. Now let's see what we got. If we look at this order, 0, 1, 2, 3, 4, 5, this is not a correct topological order. And it's because we started from 0 and we didn't know we should start from 5, which is before 0. And you can't know that beforehand. Okay. And let's look at the ending times. Also, here we started 2, 3, 4, then 1, then 0, then 5. This is not good either, because it's like the reverse. And actually, if you take the reverse ending order, the reverse order in which those ended, that will be a topological order, a correct one. And the reason why this works is, let's look, when node 1 finished, when we finish with node 1, we are sure that every one of its descendants have been finished. Because 1 cannot finish before its children. And when we go to 0, when we finish 0, all of its descendants have finished. And the same for 5, when we finish 5, all of its descendants have been finished. It doesn't matter the order in which we start, we will always get a topological order if we look at the ending times and take them in the reverse way. So if we take a look at the code, we will do the same as the depth first search. We will use the same two functions, depth first search and DFS visit. But this time we will add a global array in which we will store these ending times. We will save these in an array. And here, every time we end visiting a node, we add the key to this topological array. And at the very end, when we visited all of the nodes, we print the array, this topological array. Sorry, from the end to the start. So from the last element to the first one. In this way we'll get a topological order. But there is a case when there is no topological sort. So in this case, let's see. To get a job, you need to have experience. And to have experience, you need to have a job. So in this case, this is a loop. If you start with get a job, you can't because you don't have experience, and the other way around the same. Now, in order to check us if the graph has a cycle, we need to add an if condition. So here when we visit a node and look at its neighbors, we have to check if the neighbor is gray. So in this case, if we start from this one, we go to have experience, make it gray, but have experience has a gray neighbor. When a node has a gray neighbor, it means that there is a cycle. Alright. So we can take a variable, which initially we set it to false, and if we encounter a gray neighbor, we make it to true, and somehow print at the end that there is no topological order. It's impossible to sort. So here, instead of printing the array, we can put if there is no cycle, print the array, else print there is no topological order. Now again, that's all with the topological sort. If you want, you can pause here and do it and come back when you finish. Also, if you have any questions, don't hesitate to let me know. Alright, now the elephant in the room, this is like a pretty difficult algorithm called Tarjan's algorithm, and let's see what we have. So here we go back to graph with cycles, and the task is quite different. This Tarjan's algorithm finds the strongly connected components. So if we have a graph, it will look at all the groups of nodes which have this property that you can get from node X to any node in the component, but also the reverse. So I can get from 0 to 8, but also from 8 to 0. I can get from 0 to 1, but also from 1 to 0. So the connected components are nodes, are groups of nodes from which we can go from anyone to anyone. Here 4 is in another component, because from 4 we can get to 1 and everybody else, but from 1 we can't go to 4. So it's in another component. Same for 7 and 6. They're in different components because you can't go both ways. You can find the algorithm on Wikipedia, but also in here we'll try to put it piece by piece. Okay. The Tarjan's algorithm starts with depth first search, so it will be very similar to depth first search. We will make the color gray, we'll take each neighbor, and if it's white, visit it. Finally, make it black. And as in depth search, we'll need to start a visit from each white node in case we have separate components. Alright. So the first addition we will do to the depth search is to add an index. So each node in the node structure will have also an index integer, which will start from 0 and grow on as we pass the nodes. So the idea is to have a global variable current index. It will be initially 0, and when we start visiting a node, we set its index to the current index and increment the index. So let's see how it looks like. When we start visiting from 0, the index is 0. So we put index 0 on the current node. And also increment the index. Now it's 1, so the next node will have index 1. We color the node to gray, as we did in depth first search. Look at the neighbor. It is white, so we visit it. Again, for 3 we put index 1 and increment it to 2. For 2 we have index 2 and increment to 3. 1 has index 3. From 1 we can go to 5, which has index 4, 8 with index 5, and that's all. Now we just make them black. So basically index increases as we visit nodes. Okay, now here comes the fun. For each node, besides index, we will store also a low link. This low link will mean something like, for each node, what's the smallest index to which I can get? Let's see an example. So again, we have index starting from 0, and also low link will be initially the same as the index. So index is 0, low link is 0. Here index is 1, low link is 1. Index is 2, low link is 2. But here we have index 3, low link 3 again. But now, if we see a neighbor with a smaller index than our low link, here, so the node is not white, the node has been visited, and if the neighbor index is smaller than our low link, we update the low link to the index of the neighbor. So this will happen only if we see an already visited node. Alright, so that's the neighbor 0 doing. Now let's go to 5. 5 has index 4 and low link 4, but we see that 5 has neighbor 1. So we update the low link to its index. So now the low link is 3. And we move on to 8. Here the index and low link are 5 initially, but then we see that we have index 4 as its neighbor, so we update the low link. Now you can see that this low link isn't actually the lowest index to which we can get, because from 8 we can get to index 0, but that's not that important. It's important that if we find a neighbor with a smaller index, we update the low link. Okay, and when we finish visiting a node, the node that started visiting 8, we check if the low link of the neighbor, so after we visit the neighbor, we check if the neighbor didn't do it, so we check if the neighbor has a smaller low link. So in this case 5 has low link 3, 8 has low link 4, so we don't need to update the low link of 5, because this is smaller. Now let's look at 1. 1 finished visiting 5, so we look at 0 and 3. It's smaller, so we don't need to update it. Let's look at 2. So 2 started visiting 1, 1 finished, and we get back to 2. And its low link is 2, but 1 had low link 0. This means that 2 can get to 0. So we can update its low link to 0. If the neighbor found a smaller low link, we update it. Again for 1, do you think we need to update here? So from 3 we went to 2. 3 had low link 1, 2 had low link 0. So the answer is yes, we need to update, because we have a neighbor that can get to 0, so we can also get to 0. We make it black. For 0, do we need to update? Here we have 0, and here we have 0. So 0 went to 3, but actually here we don't need to update because it's the same. Alright, so the low link is updated when we see a gray node, actually a visited node, or when a neighbor returns. When a neighbor returns, we check if it had a smaller low link. Alright. Moving on. Finish 0, and that's it. Now we visited the whole component. Let's see how we print it. First of all, we know we found a component when the index and the low link are the same. So when we finish with node 0, we see that index and low link are the same. It's the only node so far with index equal to low link. Basically this says I am node 0 and the smallest node to which I can get is 0. So this means that I can form a component. Alright, so in order to print a component, we need to save it, to save every node we visit in a stack. The idea is we take an array and a size which is initially 0, and when we start visiting a node, we put it on the stack. So let's see how it works in this case. Initially we have an empty stack with size 0. When we start visiting 0, we put it on the stack and increment the size. When we start visiting node 3, we put it on the stack and increment the size. And so on. With each node, we put them on stack until we have the array of all of the nodes of the component. So each node is added to the stack. Now, when we get to a node which has index equal to lowling, which forms a component, we can print it. So the way we print the component is look at the stack and always print the last node and remove it until we get to the current node, which has index equal to lowling. So if index equals to lowling, we do a while loop while the last element on the stack isn't our node. We print the key of the current node and remove it from the stack. So basically here we'll print 8 because it's the last element on the stack and remove it. Then we print 5, then remove it from the stack. And we print 1, then 2, then 3. But at the end, we see that the while condition stops when the last element on the stack is actually our node. So the current node was not printed and removed. So we need to add it manually. So the last node, print the last element on the stack and decrement the size. Alright. So I know this is a lot of information and this might seem horrible, but don't worry, let's make a recap. So the whole idea of Tarjan is start depth first search from a node, visit everything we can and give each node an index, compute the lowling, which is the smallest index we can get to, and in case the index and lowling are equal when we stop visiting a node, when we end it, then we print everything that's in the array down to our current node. So here we'll print 851.230. Long stuff, long stuff. Alright, so the question is, can we start coding? So can we write this algorithm? And the answer is not quite yet. There is still one issue. So the issue starts when we go further. So we start with 0, we do everything and the component is printed out just fine. But next we should start a visit from 4. Should start visiting the next component. So let's see. We put index and lowling 6 as we should. Make it gray. And then we had look at the neighbor, and we have if the neighbor has already been visited. So if the neighbor is white, we visit it. But in this case, it's not white. So we go to the else. And we check here, is the neighbor index smaller than the low link? And here the index is smaller than the low link, so we update the low link to 3. So here it's true that from 4 we can get to index 3. But the issue is, if we do this, nothing will be printed, because this is not a component, it has index different from the low link. So here the issue was that we saw the neighbor 1 with a better index, but neighbor 1 was in another component. It's not in the component of 4. So in order to fix it, we need to ignore 1. Since 1 is in another component, it's not in the component of 4, we can ignore its index, not update the low link. So here we can add a check. If the node was visited and the neighbor is in the same stack, in the same component, then only then we check the index. Only look at visited neighbors from the current component. And if we do this, the index and low link of 4 will remain the same, and 4 will be printed as a component just fine. So this will work. Only we need to add this condition. So if the color was white, we are sure it might be in the same component, but if the color is gray or black, it might be in a different component. We only care if it's on the same stack. So in order to implement this, one way is to add an on-stack boolean in the structure. So each node will have an on stack, which can be true or false. Since we visited all of them and they are no longer in the stack, they will be false, and only 4 will have on stack true. Now, to check if a node is inside the stack, we can use if node on stack. When we add a node to the stack, we make its on stack true, and when we remove a node from the stack, we make its on stack false. So let's see where they come in the final algorithm. Here, when we add the node to the stack, we make the on stack true. And here, when we remove it from the stack, we make its on stack false. Same here. And here we have the check. So if the node was already visited, but it's in another component, in another strongly connected component, we ignore it. Only if it's on stack, we look at its index. This is a very long algorithm, but I hope it makes sense. Alright. Anyways, I'll put a link in the description with this slideshow, and it's on slide 127. I think this is the biggest presentation I've ever made. So, moving on, we have this algorithm and the data structure for each node. We have those from the depth first search, the key, the number of neighbors, and the neighbors, and the color. And for Tarjan, we need the index, low link, and the on stack boolean. And we also need the Tarjan function, which initially makes all the nodes white and mark that they are not on the stack. And for each white node, we call Tarjan visit. This is quite a journey, this algorithm. Also, I didn't put braces, which are in C or C++, because it will make the code even bigger, but you need them, so don't rely only on tabs. Alright. After you finish with all of this stuff, with depth first search, topological sort, and Tarjan's algorithm, we need to do the evaluation, which is to count the operations only for depth first search. We don't care about the performance of topological sort or Tarjan. So similarly to the previous lab, we will have two tests. First, we fix the number of nodes to 100 and take the number of arcs from 1000 to 4500. So fixed nodes, we see how the performance decreases with edges. So here from this chart, we will see the complexity with respect to the number of arcs or edges. Here in the PDF it's 9000 arcs, but I don't really care. And in the second part we'll need to vary the number of nodes, to change the number of nodes from 100 to 200 with an increment of 10, and keep the number of arcs fixed to 4500. And from this we can figure out the complexity with respect to the number of nodes. So you will have two charts, one for nodes and one for edges. And the final complexity can be the sum of the two complexities. So the sum of, I don't know, e squared plus n squared, or their product, e squared times n squared. You need to figure out which one is it. Alright, and here in this lab, the graph doesn't have to be connected, because we visit for each not visited node, we do a new depth first search. So it's not like the previous lab where we had to connect 0 with 1, 1 with 2, 2 with 3, and so on. You can choose randomly all of the arcs. So all the 4500 arcs can be completely random. And also don't forget that the graph is directed. So if you have arc 2, 7, it doesn't mean that we also have the arc 7 too. Alright, that's all. Thanks for staying with me, and I hope it helped you. And if you have any questions or issues, let me know. Have a good day. Bye bye.